Okay, so we're going to try to find the inverse of this. Now, just technically, I can say y equals x squared minus x, but just so you know how the formal notation might be. It might say f of x equals that, then it's going to say f inverse of x, meaning what we're going to get out of it. Okay? Now, for right now, I don't even care about the function itself, what it looks like. I just want to get algebraically what it's going to be. So, step one, always write in the form y equals x squared. So we have a y. Now typically you would flip out your x and y now, but it's not going to work out that way. If you see what's going to happen ahead of time, there'll be an x, that'll be too many y's, so we can't do it that way. So we're going to do a process called completing the square, and we're going to get it back in a vertex form, then we can flip it around pretty nicely. So if I write plus 0 here, that you don't need, but it kind of sets you up. So typically we would balance our c value, but nothing happens. Now I'm going to divide by my a value, which in this case nothing happens. So now I have y equals x squared minus x. I'm going to put 1's in right here. This is where I take half of b. That's b. So I'm going to say negative 1/2 squared, and I'm going to get 1/4. Okay? So if that's b, half of that, we're going to square it, and I'm going to add it to both sides. So now I'm going to have y plus 1/4 equals x squared minus 1x plus 1/4. And we're on our way. We're going to now take this trinomial and change it to a binomial squared. X, steal that sign, take the square root of my new c value when I get 1/2. Squared, take the original a value, drop it, in this case doesn't mean anything, and multiply the left side by that same a value. So right now, if you see, this would be something called the vertex form. Okay? But if I want to take that vertex form and put it into, find the inverse of that, I'm going to flip my x and my y. Okay? Now, I'm going to add 1/4 over. So if I have x plus 1/4, that is now equal to y minus 1/2 squared. Now there are a few ways to deal with this. I think looking ahead tends to make things easier, but right here I can anticipate taking the square root. Now that's going to be an ugly little thing if I'm not careful. So, I'm going to call this 4x force, if that makes sense. And I'm also going to call that 4x plus 1 force. Okay? Again, anticipating taking the square root here. When I square root this side, and I square root this side, okay, what happens is, just 1 second, I'm just writing it separately here. The square root of that stays, the square root of that becomes 2, doesn't it? Give me 1 more second. Okay, so now we're back to what we expected it to be. Now, since I took the square root of that, it's going to be plus minus, and I'm going to add 1/2 to it. And I'm going to say y equals, and I'm done. That is the inverse, okay, parabolic inverse. Now, if I had to think of I don't know, values to plug in. Let's just do a quick X, Y, Y chart. If you were asked to graph this, you know, there are a couple ways to do it, but just directly, why don't we pick a nice number like 2? Now the reason I picked 2 is because I have 4 times 2 is 8, 8 plus 1 is 9, the square root of 9 is 3, right? So now I have 1/2 plus or minus, that's a 3, right? 3 over 2. Maybe better written as 1 plus or minus 3 over 2. So 1 plus 3 is 4, divided by 2 is 2. 1 minus 3 is negative 2, divided by 2 is negative 1. So I have an xy of 2, 2, and I have an xy of 2, negative 1. Now if I'm plotting this on a point, I'd have 2, 2, and I have 2, negative 1. And I could continue. Let's say I wanted to pick another point of 0. Well, if I want to pick 0, 4 times 0 is 0. 0 plus 1 is 1. The square root of 1 is 1. So now I have 1 plus or minus 1 over common of 2. And here we go. 1 plus 1 is 2. 2 over 2 is 1. 1 minus 1 is 0. And we get this. So 0, 1, and then 0, 0. And I'm on my way to figuring out my parabolic inverse. Okay? But that's how you do it. That's a formal form of it. I could write that over too, just more cleaned up, but there you go. Okay? Next problem. we have an absolute value function. Now these are a little tricky to get the inverse of. Just quickly, let's just sketch out an idea. Okay. Sometimes it's easier to visually see it first. Let's just go like this for a second. Now, as with translations of any function, when they're written like this, we're going to do opposite, same. So -1, -3. -1, -3. I can kind of verify. Yeah, it's looking pretty good. Now we know what's going to happen. Now I'm not nice and neat, and I wish I was. But we know it's going to kind of look like this, don't we? Because it's going to be the reflection over the y equals x function, identity function. But let's just see what happens now. So as we did before, we're going to flip x and y. So I'm going to say x equals absolute value of y plus 1 minus 3. Okay? I'm going to add that 3 over. I'm going to say x plus 3 equals the absolute value of y plus 1. Now, with any absolute value equation, we're going to have two different possibilities. So what I'm going to do first is say y plus 1 is equal to x plus 3. But the other possibility is equal to the opposite of this side. So I'm also going to have y plus 1 is equal to negative x minus 3. And I'm going to solve these out. Well, if I minus 1 from both sides, I wish I had a different marker. I don't think I do. Yeah, anyway. So if I minus 1 from both sides, I get y equals x plus 2. Put a box around that. If I minus 1 from both sides, I get y equals negative x minus 4. So if I go to look at that, I do have a marker. Hold on. If I look at that graphically, if I go to see that, I start at 2. 1, 2. It says up 1 over 1. So I get something like that. Well, it's kind of looking like I'd expect, isn't it? Now I look at this one, and I start at negative 4. 1, 2, 3, 4. And it tells me to drop 1 over 1. And I get something like well, I wish that was neater. 1, 2, 3, 4. Okay. Now, let's see what I can do here. We see some stuff over here that doesn't make sense. So what we have to realize is we have a system of equations. Okay? We clearly see the reflection part, and we've got a system. If I say that y equals this and y equals this, I'm going to use substitution property and say, can't we say x plus 2 is equal to negative x minus 4? And I'm going to solve. I'm going to add x to both sides. I get 2x. I minus 2 from both sides. Looks like I have a negative 6. Divide by 2, divide by 2. I get x equals negative 3. Now definitely it's not equals, and my graph isn't perfectly accurate. I didn't have graph paper with me. But we know x has to be greater than negative 3. So technically I should have been out here a little bit more. And x is going to be greater than or equal to negative 3. And the only way to describe this technically correctly is with a piecewise linear. So let me do that real quick. So I describe this by saying f of x, or technically f negative 1 of x, because I'm graphing the inverse of it. And we're going to say is equal to x plus 2, negative x minus 4, if x is greater than or equal to negative 3. And we're done that one. Okay, I'm going to do one more while we're right here. I know you were wondering. Here. Now, that is a confusing little creature. After a while it becomes more natural to you, but right now it just looks like a mess. So if I said find the inverse of that algebraically, f of x, f negative 1 of x, I am going to do the following. Now if you look at it, you're like, oh, we came up to that problem recently. If I change that to x and this to y and y, I'm in trouble. I got too much stuff to look at. One of the easier methods to use is long division, and we're going to look at it differently and then decide what to do. Okay, so if I long divide that, bottom into top, x minus 4 into x plus 1, x goes in x, 1 times x is x, I get negative 4, and 1 minus a negative 4 is 5, right? That's the remainder portion over the original divisor, and I modified that to look like this. and it looks like it's hyperbolic, which I won't have you graph right now, but algebraically. So why don't we say we have y equals 5 over x minus 4 plus 1. Okay, now not that you care right now, but if I'd said quick, let's get a sketch. 4 to the right, up 1. So 1, 2, 3, 4, up 1. I have a vertical asymptote at 4. I have a horizontal at 1. Positive k value indicates branches in the first and third quadrants, so I get the idea. I should expect to see something over here. Okay, so now I'm going to flip my x and my y, and I'm able to do that. So if I have x equals 5 over the quantity y minus 4 plus 1, I'm going to solve for y. I am going to get my purple marker. I'm going to minus 1 from both sides, right? Minus 1, minus 1. Now I have x minus 1 equals 5 over y minus 4. Now that y is tricky because it's in the denominator. So I am going to multiply both sides by that same quantity, y minus 4. Now sometimes after a while you can do this right in your head, but I'm just showing you out to make sure. That cancels out. Since I want y eventually by itself, I'm going to divide both sides by the quantity x minus 1. That leaves me with 5 over x minus 1 equals y minus 4. Y equals, add 4, and we're done. This is the algebraic inverse. I guess while I'm here I will graph it because I'm so close. Vertical asymptote at 1, up 4. So if I'm at 1, and I'm at 4, 1, 2, 3, 4, and I get the same parent function, branches 1 and 3, you will see one side mirrors the other side. And there we go. Those are 3 of the tougher inverse functions, and actually the parabolic inverse wasn't really a function, but you get the idea. Okay, good job.